In this lecture, we're going to talk about the second half of section 10.5 on planes. Now, a plane is a two-dimensional set of points that is flat, living in three-dimensional coordinate space or potentially higher dimensional coordinate space. And it is characterized most strongly by what's called a normal. This vector right here, which is perpendicular to the plane. The plane is this flat expanse, and if you point sort of straight up from the perspective of living on the plane, that direction is called the normal direction, and that direction is the same everywhere on the plane, so it very much characterizes the plane. If we have the normal and we have the point x naught, which is simply some point on the plane, it can be any point on the plane, then we can uniquely define the plane. Basically, the argument is that if I have a given point in the plane, x naught, then if I make a line segment to any other point in the plane, x, that line segment will be perpendicular to the normal of the plane, no matter what x naught is and what x is. So we can express this relationship mathematically. Here is any point in the plane, x, the vector, coordinate vector x, y, z. And then this is the point x naught, which is a specific point in the plane. And the difference between those two vectors is the line segment from x naught to x, right here. Actually, this blue line here. And then the definition of a plane is that for any point x in the plane, that line segment is perpendicular to n. And so we say dot n equals 0. And this short little equation right here characterizes a plane, defines a plane with a given perpendicular normal n and member point x naught. So that's it. We can write this out in a little bit longer form if we feel like it. Suppose n, the normal vector, has components, we can call them ABC for the x, y, and z components of the normal vector. Then we can write this out kind of in a longer form, ABC dotted with the coordinate vector x, y, z, and then when we distribute that dot product, we also get minus ABC dotted with x naught, y naught, z naught equals 0. And we can write this, which is a slightly long form of the standard equation for a plane. Or if we simplify this a little bit and we let negative a x naught minus b y naught minus c z naught, and we take that number, this is just a set of constants ABC and another set of constants x naught, y naught, z naught, and so that's just going to be some number d. Then we can shorten this definition to the second line here, ax plus by plus cz plus d equals 0. And the thing that it's really important to note from a practical perspective is that the normal of the plane, if the normal is defined by the coordinate vector ABC, you can read the normal ABC right off of this standard definition of a plane. So if you're given this equation in this form with some set of numbers, and they say, what's the normal of the plane? You can just read it off, ABC. Or if they say, construct a line that's perpendicular to the plane, well, if a line is perpendicular to the plane, that means it's parallel to the normal, and there's its direction vector right there, ABC. So this is, it's a reasonably short equation that expresses a reasonably large amount of information, and it's called standard form. So really the rest of this video is just examples using planes and sometimes using lines in planes. So the first example is illustrating the idea that 3 points make a plane. Really, 3 points make a triangle in space, but a triangle is a two-dimensional object, and if you imagine extending that flat region in all directions away from the triangle, then you get a plane. So 3 points in space, as long as they're not collinear, are enough to define a plane. So given 3 points, how can we construct a plane? Well, what do we need for a plane? We need a point and a normal. Here we're given 3 points, so there's no shortage of points, but we don't have a normal. So the normal is perpendicular to any line segment in the plane. And from these 3 points P, Q, R, we can construct 3 different line segments that are all in the plane. So what we need is we need a vector form of these line segments, and then we need something that is perpendicular to 2 of them. And we have exactly the tool for that job in the form of the cross product. So you can construct these 3 segments any way you like. I've used P as a common vector tail, and then PQ is one vector and PR is the second vector. So I take Q minus P, gives me 3, 3, 3, and R minus P gives me 5, 3, 1. And now I take the cross product of these 2 vectors, and I plug these numbers into my formula, or I look up on my formula sheet the longer form of the cross product formula. I do my computation, I get a vector, -6, 12, -6. And that is a normal to the plane, and I can plug that normal and any one of these 3 points, P, Q, or R, into the formula for the plane. Here I've just started straight from the vector form, vector definition of the plane. I haven't tried to memorize anything except this geometrical definition, which sort of conveys the most geometrical information. I plug in my coordinate vector xyz minus the point in the plane 1, 2, 3, dotted with the normal -6, 12, -6, and then I do some algebra, and I get the following representation of the plane. Here we find that D is 0. If D is 0, that means that the point actually goes through the origin, because you can plug in x, y, z, 0, 0, 0, and satisfy this inequality. I have not tried to simplify this at all, but I would like to point out for your benefit that you can simplify this expression and get the same plane. So this is entirely equivalent to the plane -x plus 2y minus z equals 0, which means that an alternate normal, we could have chosen to simplify this normal itself to be -1 to -1 if we prefer small numbers to large numbers. This is the same plane. This is just a shorter version of the normal, and the plane's definition does not depend on the length of the normal. So these are entirely equivalent. You may choose to simplify your answers, your equations for planes, if you like. Another example. Suppose I'm given a line and a plane. Do they intersect? And if they intersect, where do they intersect? So just because your textbook occasionally uses symmetric form, I have used symmetric form here. To be honest, I'm not really sure why. As I've said, I think symmetric form is kind of silly. But nevertheless, you have book problems that contain this, so we'll do a problem like it. So here's a symmetric form of the line, and we're given the same plane from the last problem. If they intersect, where do they intersect? So, again, before you start these problems, you want to just not rush to write down a formula, especially if you're rushing to write down a formula from a problem that you think might be similar. That is a recipe for disaster. We've got to stop, we've got to think, and decide what are the right tools for the job in each of these cases. And so here, what is the key idea? It's that if a line and a plane intersect, then at some point, they occupy one point in space in common. At least one point. If they intersect, it's one point. If the line happens to lie in the plane, it could be an infinite number of points. And if they're parallel, then they wouldn't occupy any points in common. But suppose we assume that there's one point in common, we're looking for it. Then we take the representation of the plane. We try and find that point that they occupy in common. So the first thing we're going to do, I'm sorry for getting a little distracted here. The first thing we're going to do is we're going to convert symmetric form to parametric form. Okay, what does symmetric form mean? It means that if you had the parameter t in your line, each one of these things would be equal to t. That's how we got symmetric form. So to convert back to parametric form, we can set each of these 3 expressions equal to t. T equals x minus 2 over 3. That gives us x equals 2 plus 3t. The second expression gives us y equals 5 plus t, and the third expression gives us z equals 1 plus 2t. So these equations must be true if we're on the line. And if we're on the plane, this equation must be true. So to be in both, we must have to satisfy all four equations at the same time. And it looks like in general this is likely to be the case because there are four equations and there are four variables. X, Y, Z are the coordinate variables and then T is the parameter, which in principle is another unknown. So at least from a dimensionality perspective, in general, this might be expected to work out. So to solve these four equations for four unknowns, we can take advantage of their structure. The plane equation has x, y, and z without any t's, and the parametric equations for a line define x, y, and z all in terms of t. So in general, we should think of this as a 4x4 linear system, but this one is particularly easy to solve by replacing each of the x, y's, and z's in the plane with the parametric form given above. So we do that. We substitute in the parametric equations, -6 times 2 plus 3t, plus 12 times 5 plus t, minus 6 times 1 plus 2t is now the plane equation with the variables replaced. And that gives us one equation for the one parameter t. We write that out, we simplify, and we solve for t, and we get some number. All right, now the problem asks us to go a little further, not just find the value of the parameter, but find the location of the point. So how do we do that? We need to plug this value of t back into the parametric equations for the line to get the point of intersection. So we do plug in t equals 7/3, and we get a point in space at which the line and plane occupy the same point. Now, this was a problem where the line and the plane did intersect. We found one point of intersection. You may try and solve these equations and find there is no solution. That means the line and the plane are parallel. And if there is no solution, then you would find that the direction vector for the line is perpendicular to the normal vector for the plane, which makes the line and plane parallel with no points in common. Another possible outcome when you're doing this kind of problem is that you find there are an infinite number of solutions. When you get to this step up here where you have a single equation for t, you just get 0 equals 0. That means any point t is acceptable, which means the entire line is in the plane, and that just means that the line and plane are coplanar. The line is just a subset of the plane. It lives in the plane, which is technically possible. Okay, another example. We might be asked to find the distance from a point to a plane. And this is a problem that does involve lines because the distance will be the distance over a line segment, and we'll have to find that line segment to solve the problem. So here we're given a point, P, somewhere in space, and this same old plane again that we've been using for our last couple example problems. So the key idea here is that the shortest distance from a point to a plane is perpendicular to the plane, right? Imagine going instead to some other point R whose angle with the plane is not 90 degrees. Then you could always move that angle closer to 90 degrees and reduce your distance to the point P. And so, therefore, the shortest distance is perpendicular to the plane. So, we're given a point P. Then, the direction vector of the line segment, that is the shortest distance from P to the plane, will be parallel to the normal of the plane in order to be perpendicular to that plane. So that gives us a direction vector. So we have the point, we have the normal, which is our direction vector, which we sometimes call V in other problems, but here it's a normal. And that gives us a line and a plane. And we just did a problem where we calculated the intersection between a point and a plane. And that will give us the point Q, and then we find the distance between P and Q. So, multi-step problem. Always, it's important to think through the process before we start writing down formulas and trying to calculate things. So what's the first step? Write down a line through P with direction N. All right, so here's our point P. Here's our direction vector N. And so here's our vector form of a line. And here's our parametric form. X, the component of R, the first component of R is the variable X, equals 0 minus 6t. Y is 4 plus 12t, and Z is 2 minus 6t. What about the plane? We plug these equations into the equations for the plane, and we get one equation for the parameter t. And we do that out. We distribute our normal components, and we solve for t, and we get some number. So now we have the value of t where the line segment intersects the plane. We find q by inserting t is minus a sixth into vector form of the line, and we get the point q. So now we have p and q, and we find the line segment between them by subtracting one from the other. That gives us the point 1, negative 2, 1. And the magnitude of that is the distance from the point to the plane, square root of 6. In your notes, you'll find another page that contains a little bit more circuitous argument for calculating the distance between a point and a plane that ultimately produces a formula. And you guys will be very excited to have a formula for this kind of problem, but I really prefer encouraging you to think through these kinds of processes in geometric terms. Straightforward, direct, step-by-step process. What do I know about the shortest distance? Oh, it's perpendicular. Do I have that direction? Oh yeah, it's the normal to the plane. So I can construct a line. And then I know how to find the intersection of a point, a line and a plane. And I know how to calculate the distance then between the resulting 2 points. So I will go ahead and distribute that section here, this page right here, in the notes. But I won't go over it here in this video. You can review it at your leisure and see how you feel about it. Last example in this section, intersection of two planes. If two planes intersect, they have a line in common. This makes sense. A plane is one equation. There are three unknowns, x, y, and z. A plane is one equation, and so one equation between three unknowns leaves you 2 degrees of freedom. That's why a plane is a two-dimensional object. But now if I have two planes, the intersection of these planes would require both equations to be true at the same time. I'm in the first plane, so the first equation has to be true, and I'm also in the second plane, so the second equation has to be true. So now I have two equations between three unknowns. That leaves me 1 degree of freedom, and I would expect the answer, the result, to be a one-dimensional object, i.e. a line. So what can we say about finding this line? In general, like any line, we need a point and a direction. The direction is a little bit easier to obtain because if I'm in the first plane, which I am, then I'm perpendicular to the first normal. And if the line is also in the second plane, then it's also perpendicular to the second normal. So the direction vector of my line will be perpendicular to both the normal n1 and the normal n2. And again, if I need a vector perpendicular to two other vectors, I have a tool in my bag that does just that. It's the cross product. So I compute n1 cross n2, and I get a direction vector v. Here, 24i minus 24k. Again, the direction vector of a line does not need to have any certain magnitude. So if you prefer, you could simplify this down to be simply 1, 0, minus 1 is an acceptable direction vector. It is also perpendicular to both n1 and n2. I think I've gone ahead and used 24, but that's fine. They both give the same answer. So now we have a direction vector. The last thing we need is a point. And this is not trivial, but we can work our way towards finding a point on this line. So here's the idea, is that this direction vector here has a component in the I direction and a component in the K direction. And so we're going to be multiplying this direction vector by t. And so both x and z will eventually take on all possible values. You'll be adding arbitrary multiples of 1 to the x variable and arbitrary multiples of -1 to the y variable. So both x and z will explore all possible values. In particular, z will somewhere be 0. There will be some point on this line where z is 0. And that's because this number right here is not 0. All right, so that's good enough. All I need is one point on the line. It doesn't matter where it is. So let me look for that point. That point on the line where z equals 0. This is somewhat of an arbitrary choice, but it just makes the algebra a little bit simpler. So go ahead and plug z equals 0 into the equations for the planes. Go back up here and just plug in z equals 0. Cross out these terms. And that gives me simplified equations containing only x's and y's. And there's two of the equations. So now there's two equations for two unknowns, a 2x2 system, which allows me to find x and y. So I work through this 2x2 system, I find the answer, and I get a value of x and a value of y as a solution. I also know, because I assumed it at the beginning, that z equals 0. And so the point -5, -5/2, 0, is a point on the line. And so that's good enough. I just take that point and the direction vector that I just found multiplied by t, and that gives me the equation for the line of intersection between these two planes. Couple of notes. This arbitrary setting of z equals 0, as I tried to describe, is dependent on the direction vector of the line not being 0 in the z component. For instance, I could not have said, let's just let y equal 0, because the 0 here in front of j means that y is not changing. When I multiply by t, y isn't changing. And so if the value at, the whole line has the same value of y, and if I randomly assigned y equals 0, that would probably be incompatible with the definition of the line. So that's one note. Another note is that if you try and find the direction vector of the line, you take the cross product of the two normals of the planes, you might get 0. What does that mean? That means that the normals are parallel, which means that the planes are parallel. Okay? And if the planes are parallel, probably what that means is that they don't intersect at all, and so there is no line of intersection. But this can also be problematic if they are in fact the same plane. Then they share an infinite number of points in common, not just a line. They share each other in common. So the intersection of the planes is in fact the planes themselves, not another line. So these are kind of edge cases that you won't encounter very often, but you might see such a problem, and if you ever know that you're doing it correctly and yet you get 0, that's what that means. So that's all. Lots of examples. Not a whole lot of new concepts, but planes are very common objects, and so it's important to spend a little while understanding how they're defined and how they work and how we work with them. See you in class.